Hi, welcome to the final video in vectors, higher maths, properties of scalar products. Okay, and again, it's just one thing we're doing here, using the properties of scalar products to simplify and calculate more complicated scalar products. Now, you'll do lots of practice, and this is where a lot of kind of tricky exam style questions come in. But there's two things I'd like you to just to be aware of. Firstly, that it doesn't matter what order you multiply or do your scalar products in. And secondly, the brackets work exactly the same way with scalar products as they do with normal algebra. Okay, and again, teachers should show you that in terms of the proofs behind that. They're definitely two you should see. So I'm going to do two examples. First one here, again, sorry, just give it a wee pause and copy that down. Example one here. We're looking at three different vectors, and we're looking to calculate a dot b plus c. Okay, now because we know the values of b plus c here, we can do that. We can calculate b plus c first and then dot it with a. But an alternative is to do a dot b plus a dot c. Okay, so a dot b, just looking at a and b from your eyes, is 2 multiplied by 5. Add from your j's 4 multiplied by 3, and then add from your k's 3 multiplied by 6. Okay, so that's going to be 10, add 12, add 18, so 22, 40. Okay, but we also have to add on a dot c. So from your i's, 2 multiplied by 5, add from your j's 4 multiplied by 6, and from your k's, 3 multiplied by -1. So that's going to be adding on 10, add 24, so 34, subtract 3 is 31. So your a dot b plus c is 71. Okay, now obviously because you know the vectors there, you could do it both ways. You could do b plus c and then dot it with a, or you can do a dot b plus a dot c. Okay, but that's showing you how it works in terms of breaking the brackets and then just treating with each as a normal scalar product. Now, with this second question here, we do not have the luxury of being able to do it both ways. We're going to have to do it by multiplying out the brackets. Take a wee pause of the video, try it. Okay, so firstly, we've got to have a look at a couple of things. Triangle PQR is an equilateral triangle. So first things first, because it's an equilateral triangle, I know each of the angles is 60. And then I need to find, oh sorry, the sides 3 units. So magnitude of A, B, and C is all 3. And I want to find A dot B plus C. Okay, so A dot B plus C, I know, breaking the brackets, is going to be A dot B plus A dot C. Okay, now I don't have the components, so I can't just do multiply and add. I need to do the magnitude of A multiplied by the magnitude of B. Probably a bit messy. Cos angle, I'm just going to call it theta1 just to separate them because they may be different. Plus the magnitude of A times the magnitude of C cos of theta2. Okay, so A dot B is going to be 3 from the magnitude of both cos of 60. And then I'm going to add on, well, A and C and magnitude is both 3. But we have a wee issue here because we're doing A dot C. A and C, they both don't leave the same place. They don't leave from their meeting point. A approaches the meeting point and C leaves it. So what I'm going to have to do is move A up to here. Okay, so it's still going to be 3, that's fine. Magnitude of C is still going to be 3 as well, but the angle in the middle is going to be 120 degrees. So it's 3 times 3 cos 120. Okay, and then we can just calculate it. 3 times 3 cos 60 from our exact values is a half, so that's going to be 9 over 2. Okay, and then cos 120, I'm just going to do a little bit of work at the side here for cos 120. So cos 120, looking at my cast diagram, 120 is in the second quadrant where cos is negative, so it's going to be a negative cos. and the equivalent angle in there, we're coming 60 degrees back to get to 120. So it's negative cos 60. No, we just found negative, just found cos 60, so it's just going to be negative a half. Okay, which means we're going to be adding on negative 3 times 3 times negative half, so we're adding on negative 9 over 2. So 9 halves add negative 9 halves is going to be 0, which is interesting because we know something about a dot product equals 0, don't we? If a dot product is equal to 0, we know the vectors have to be perpendicular. But the question here is, what vectors are perpendicular? Now the dot product you're doing is A dot B plus C. So A dot B plus C is equal to 0. Therefore, A is perpendicular to the vector B plus C. Okay, so because it's equal to 0, A is perpendicular to B plus C. Now that's a much trickier question using this, the distributive law. Okay, but things to be careful of, again, make sure your vectors are leaving the point. And then just there, that's just kind of a wee quirk of this question, the fact that because it's equal to 0, you have to go right to the start and say, well, that means that is perpendicular to that. Okay, again, any issues, give us a shout. Thank you.